We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Channel.
I want to present to you the team that has brought us back to Mars tonight.
It was another giant leap in space exploration. The safe landing of arguably the most sophisticated probe ever sent to another world. The Mars Rover, aptly named Curiosity. It took 10 years and billions of dollars to build and send into space.
3 or 4 meters.
That's awesome!
Curiosity was seeking answers to some of the most profound questions. Did life ever take hold on Mars? And could it exist there still?
Are we alone? I think it's the grandest of all scientific questions.
Look at this!
A series of probes have revealed intriguing details on a planet that has proved to be more dynamic than the experts ever imagined. Curiosity is the most advanced craft ever sent to Mars.
We go exploring because we are curious creatures, human beings.
We want to discover the unknown. Going to Mars is like the new frontier.
This will be the most exciting adventure we've ever undertaken on Mars.
Its payload was 10 times more massive than anything that had gone before. A roving laboratory that would deliver stunning details about the potential for life on Mars. It was an all-or-nothing moment for hundreds of people who had dedicated their careers to a pioneering mission. They were responsible for a $2.5 billion probe that hurtled into the Martian atmosphere at more than 20,000 kilometers an hour. Most Mars missions ended in disaster. A failed landing would also send careers and the reputation of America's space program crashing into the dust. But the potential prize was worth the considerable risk. Mars is a world that could hold vital clues about the evolution of life and our place in the cosmos. Its unique geography is also worthy of exploration in itself. The largest known canyon on any planet slices across its equator. Mars is also home to the tallest volcano in the solar system, towering some 25 kilometers high. But its beauty belies an ugly reality for any potential visitors. Mars has no magnetic field or substantial atmosphere to deflect radiation. Its surface is constantly bombarded by deadly solar and cosmic radiation. The thin atmosphere retains little heat. The average surface temperature is a frigid -53 degrees. Liquid water would vaporize or freeze instantly on Mars today. And yet, flowing water appears to have left its mark all over the red planet, including river valleys and flood deltas.
Most experts would agree that 3.5 to 4 billion years ago on Mars, There was probably significantly more water in lakes, as flowing rivers at times. To some extent, Mars is like a twin of Earth early in its history.
If Mars was once awash with water, it means that life may have thrived, and maybe still does, in some hidden sanctuary. It's these stunning possibilities that lead experts back to Mars over and over again. NASA's latest mission was built around the most complex robotic spacecraft ever sent to another planet.
I love the fact that our rover is named Curiosity, because I think that's why she exists.
You hear us talk about her as if she's a person, because to us she is.
Okay.
Curiosity was packed with custom-made instruments, able to send and receive information from controllers on Earth. Perhaps most important of all was her nuclear battery. Designed to provide at least 2 years' power on the freezing, dusty surface.
The goal of this mission is to undertake the search for habitable environments. What it reduces to is the search for 3 very simple ingredients for life itself.
These 3 ingredients are the same essentials that sustain life on Earth. Energy from the sun above, or volcanic activity below. Liquid water and organic compounds, the carbon-based building blocks of life. Like a robotic geologist, Curiosity was packed with tools to scrape, drill, hammer, sample, and analyze. It would probe the rocks and soils of the red planet, much like a human geologist would do on Earth.
When a geologist looks at a landscape like this on Earth, we're looking for a way to unravel what the early environmental history of the planet was. Now, on Mars, with Curiosity, we can do the same thing.
Curiosity's toolkit rivals that of any earthly geologist.
Curiosity has the equivalent, the MALI instrument.
The Mars Hand Lens Imager, or MALI, has a vast range of magnification.
We can focus the lens to different distances depending on what we're looking at, so it'll actually be better than this. Photography is really important because it creates a context for all of the other measurements and observations. Curiosity has 17 cameras. We've got telephoto capability, mid-range to near field, and we can also capture video.
To collect rock samples, a geologist uses a basic rock hammer.
We use it to get rock that is not exposed at the surface of the Earth for doing the geochemical analysis that tells us about the origin of the rock.
Curiosity has more advanced tools for tackling Martian rock. It's armed with a laser that can vaporize a pinhead-sized spot up to 7 meters away. It can tell what the target rock is made of by analyzing the flash of light that's released as the laser hits. It also has a more conventional drill that pulverizes and collects yet more samples for onboard analysis.
On Earth, we'd have to take the piece that we broke back to the lab to do the analysis there. With Curiosity, we bring the lab to the field.
The rover's robotic arm was designed to feed powdered rock or soil into 2 test chambers inside the rover. One uses X-ray beams to identify minerals. The other tests for the presence of organic molecules that may have been associated with life.
What's important about organic molecules is that you don't have to have an actual fossil of an organism left behind in order to detect the former presence of life. So we're not doing life detection, but we can look for these organic compounds.
Curiosity would herald a new era of exploration on Mars.
This is the mission that really advances our knowledge of Mars in a way that we just weren't capable of doing in the past. We're taking 15 times more scientific equipment with us this time, and therefore the rover that drives that around on Mars has to be that much bigger.
Weighing nearly 1 ton, getting it safely on the surface presented another unique challenge.
We knew we needed a new landing system. We've never landed anything this big on Mars before.
There was a tried and tested landing technique that had worked for previous missions. Probes were packed in shells. Heat shields protected them from the searing temperatures of entry into the Martian atmosphere. Parachutes slowed them down, but the atmosphere was too thin to slow them enough. Giant airbags were deployed to bounce them to a gentle stop.
But as it turns out, this rover was essentially too big to make airbags be the right solution. We looked at that and the airbags wound up just being big and heavy. So we said, okay, let's come up with something else.
A rocket-powered descent on a lander with legs harked back to the Apollo moon landings.
That's how you're supposed to do it. You're supposed to land with your rocket below you, climb down the ladder, and explore. That's how Buck Rogers did it. That's how the Apollo astronauts did it.
But we could see a legged lander would be too top-heavy with a big rover sitting on top of it.
So we said to ourselves, why don't we turn it upside down? Let's flip it around and put the rocket on the roof and land the rover on its wheels below.
We just started burrowing in on this idea, this rocket-powered jetpack with this rover dangling down below it.
Looking at it, it's not intuitive. I think we affectionately called it hope on a rope at one point.
We're using flight spare.
But the uniform's like
westward looking to do that first.
Billions of dollars and the credibility of NASA's space program was at stake. The plan was to pack Curiosity into the typical protective shell and deploy the usual kind of parachute. But with just a mile to go before it hit the surface, the rover was to be released and its rocket-powered lander fired up, controlling the descent. The lander would then gently lower Curiosity to the Martian surface. On touchdown, the cables would be cut and the so-called descent stage blasted up and away to crash elsewhere. The entire sequence would take just 7 minutes, but every stage required split-second precision.
Literally, millions of little things have to go just right, like a chain, where success is at the bottom of the chain, or it's just game over.
Designers hoped a simple video would convince their bosses to embrace the new hope on a rope landing technique.
Some of our NASA bosses, they just were in horror after seeing this video.
It's the kind of thing that you wonder if they're going to be taking odds on it in Vegas.
The landing sequence, it's just like surreal of like, really, we're gonna do that?
Probably the biggest challenge in the Skycrane system was credibility. Trying to convince people that the Skycrane system was not an insane contraption, but was actually a very elegant piece of machinery.
But just testing the process was a challenge in itself.
Here on Earth, you cannot test the one large simulation that takes us from above the atmosphere down to the surface of Mars. Not the right atmosphere, not the right gravity.
So we have to break the testing down in lots of little pieces. And by looking at these little individual parts of our testing, convince ourselves the whole will work.
Testing took years to complete, and there was still no guarantee that it would work. The massive parachute was just one part of the complex landing kit needed to get the 1-ton Curiosity rover safely on Mars. The parachute would have to withstand a staggering 30 tons of force. It was sent to the world's largest wind tunnel.
We felt confident that the parachute was designed correctly and that these tests would go smoothly.
Their confidence seemed justified at first.
3, 2, 1, fire!
Parachute opens, a building shakes, and you see this thing flying in the air, and the data, and everybody's excited, and it's tremendous.
It seemed that the second test was a mere formality.
3, 2, 1, fire! Bad shoot. Oh.
Catastrophic failure. Blew up. Little pieces of parachute all over, and this is a bag of rags at the end of the tunnel.
Parachute is, it's a loss.
It's almost like you lost a friend or something, a fallen comrade in the wind tunnel. And it caught us by surprise. We didn't expect that.
Such a failure above Mars would mean disaster.
That basically kicked off a forensic test program to figure out why that parachute exploded so catastrophically, and was this a threat to the Mars mission?
The catastrophic failure was caused by so-called inversion. It happens when one side of a parachute slips through the other. The resulting pocket inflates, pulling the parachute inside out and tearing it to pieces. It was something they had to rule out for the descent to Mars.
We have just as high a risk of an inversion.
They studied the videos for months.
This is much less organized than it is here.
Before a critical factor became clear. The parachute took much longer to inflate in the wind tunnel than it would above Mars.
On Mars, when you pop out your parachute, a second later, it's open. In the wind tunnel, it takes 6 seconds, 7 seconds, 8 seconds.
And so, waiting to fill up this bag of air, the flapping of the parachute can allow bits of it to overlap and then be pulled through and invert.
Inflating the parachute sideways also made the risk of inversion far greater.
We were deploying the parachute sideways, so gravity is pulling the parachute down. That causes the top of the parachute to fall through the bottom of the parachute.
But above Mars, the parachute would deploy upwards.
It took a long time to figure out that this was an Earth test problem, not a Mars problem. It was a real nail-biter. Since we've only got one parachute, you kind of got to get it right.
They were confident that high above Mars, their parachute would perform according to plan. But deploying the parachute was just one of a series of events that had to go right first time, with split-second accuracy. A radar system was designed to measure the speed and altitude of descent. It would determine the precise moment when the critical sky crane maneuver would start to lower the 1-ton rover to the surface. Curiosity's sophisticated radar was composed of 6 high-powered narrow-beam antennas. Each was designed to take 20 measurements a second for unprecedented range and accuracy.
We had to be able to test the radar under all the conditions that it could be exposed to at Mars. And that is a very wide range of altitudes.
The radar had to work at extreme altitude and extreme speeds. Replicating something like those extremes on Earth called for an FA-18 supersonic jet. A test antenna was mounted under the wing. The radar test pod was activated and flown some 15 kilometers above the ground before the pilot plunged into a series of death-defying dives. The measurements of speed and altitude were spot on.
1-8 Alpha Foxtrot.
Yeah.
The probe's radar system was also tested at lower altitudes, above the Mars-like terrain of the Mojave Desert.
We flew over lava flows, we flew over sand dunes.
We flew around a crater that has a lot of shapes that are very similar to what we'll see on Mars. We found that two beams, even if they're angled up and away from where the rover is going to be, were enough to tell us how fast we're moving towards the ground.
3 or 4 meters.
That's awesome!
But there was another key part of the landing equipment that had to last well beyond touchdown. The all-important wheels and suspension system had to cushion Curiosity's landing.
Do that again.
They would also have to keep Curiosity moving over all kinds of terrain for a minimum of 2 years.
Stop.
The mission depended on the landing gear that would also keep the rover rolling.
The rover touches down at almost 3 feet a second, which doesn't sound that fast. But some of those loads are 2,500 pounds going into each individual wheel, and what the wheels don't absorb goes into the suspension. We're just trying to make sure that all of those precious science instruments are safe.
The wheels and suspension needed to be strong, but also as light as possible. A simple, down-to-earth design had the answer.
If you look at the modern bicycle, they do amazing things with shaping the tubes of the bicycle frame for the stiffnesses they want in every direction. And so we talked to a bicycle company that makes titanium bikes, and they helped us build the suspension tubes.
The humble bicycle also inspired the wheel design.
We ended up taking a bicycle wheel and making it as strong as possible, taking that to the extreme and making it basically a Martian bicycle wheel.
The bicycle-based designs were rigorously tested over all kinds of terrain.
Brakes engaged, motion complete.
Sand dunes had been a problem for previous Mars rovers.
Still making progress.
But Curiosity's wider wheels did not sink in the sand.
Okay.
This is good, Adam. This is what I was hoping for.
What I'm learning here is that it's really hard for this thing to get stuck.
That's why we're here.
It was the latest of many missions to the Red Planet. A world that captivated the human imagination long before the space age.
Life forms on Mars may have developed special ways of preserving their water content.
Observers and writers imagined strange plants, even canals built by intelligent beings.
Are they planning an invasion?
We finally got the first true close-up glimpses of Mars in the 1960s. There were no structures or complex life forms. Probes sent back pictures of a bleak and barren world.
Fantastic. 16 kilobits.
NASA's Viking mission put 2 probes on opposite sides of Mars. They tested the soil for living organisms. There were no signs of life, not even a single organic compound. Mars was declared dead.
Then we kind of took a break, I think, because of that disappointment from exploring Mars for over a decade.
But the Red Planet continued to captivate researchers who took a more subtle approach. They could see dramatic features seemingly carved out by liquid water. If water had been present, then life may have once existed there. A new generation of orbiters examined the Martian surface for evidence of water.
The beauty of orbit is you can send a lot of instruments. These orbiters are pretty big. We've flown cameras that can actually measure the temperature of the surface, lasers that can measure the height of the mountains, and spectrometers that can map what minerals are present. So from orbit, we can map the entire planet and figure out where all the goodies are. This big picture orbital view really has just revolutionized how we think about Mars. There are incredible mineral deposits, rocks that formed in lakes and hot springs. We even think there might be water that's flowing in little channels today.
Probes and Earth-based telescopes also detected something else in the thin atmosphere: methane gas. On Earth, methane can be produced by geological activity, but most of it is generated by microorganisms as a waste product. But Mars has no active volcanoes. Whatever is producing the methane remains a mystery. It could be some unseen geology, or even life, thriving under its sterile surface. Two key ingredients of life have washed over Mars: liquid water and energy from the sun. Curiosity would resume the search for the third vital ingredient: organic molecules. To do that, it needed a robotic arm with the strength and precision to gather samples from Martian rock and soil.
Robotic arm is extremely complex because we have 5 joints. We have what we call the azimuth joint, which is really just kind of, you can think of your shoulder moving back and forth. Then we have elevation, which again is like your shoulder moving up and down. And then we have the elbow, which actually works like the elbow. It usually moves like that. And then we have wrist, which is just kind of like the wrist. It moves it about here. And then we have turret, which allows us to like rotate 360 in either direction. So the robotic arm, it really is an engineering masterpiece.
The engineering masterpiece had to survive a long journey through space, the extreme entry and landing, and then operate on all kinds of rugged, dusty, and freezing terrain. Scooping up samples had been done before, but Curiosity's remote drilling capabilities were unique.
We haven't drilled on another planetary body since Apollo.
Okay, Bob, I've got my tools of the trade right here.
Their drills were more challenging, that they needed to get like 1 meter to 2 meter cores, but they had astronauts that could react to the situation. Once you penetrate the surface of another planet, now you have to deal with all kinds of unknowns.
How to keep the drill perfectly clean, how to isolate it from the mechanical workings of the motors, how to not drill into a rock that will end up clogging the system so that we can't use it anymore. These are really the big challenges.
The bit was designed to drill and collect at the same time.
It's a rotary percussive drill. And that's typically what you would buy to go, to like drill through concrete in your yard or whatever. The main difference is the average person in their yard doesn't want to collect the powder. So we have a powder collection system effectively around the drill bit.
The drill bit carries powdered rock up inside as it turns. The sample passes through a sieve to filter out larger particles. Engineers had to find a way to keep all kinds of sticky samples moving through the system.
Most spacecraft, you try to keep pristinely clean, and then you try not to bang them up more than they have to. We, on purpose, shake the turret really hard, and we know we're going to get dirt everywhere. We have to get used to more violent hardware. It's more like a mining operation than a fine precision operation.
And actually, to understand how to build that drill system that doesn't shake the arm apart or shake the rover computer too much was a big challenge.
Their engineering had to be precise, delicate, and robust, all at the same time. They also had to foresee a range of potential disasters. If the arm got damaged or the drill bit stuck, they needed a way out. Once Curiosity was on Mars, it was on its own.
If, heaven forbid, the bit would get stuck, we actually have 2 spare drill bits. We would unchuck the bit, leave it there, and then we would grab another one to live another day.
3, 2, 1, go.
After years of painstaking research and engineering, they were ready to test the entire drilling and sample gathering system. The precise delivery of a stream of white powder would prove they'd got it right.
One of the kind of comedies of scale of this rover is we have a 900-kilo rover with a 100-kilo arm, and we drop off a little tiny, sample to each instrument, and that's enough for them to do their science.
There it is.
The tiniest granule of powdered rock could hold the conclusive evidence experts are after, that Mars once harbored life. The next key part of the mission was to choose a safe landing site that was also most likely to hold such evidence. Previous missions were aimed at smooth, flat terrain. But even a slight change in atmospheric density, wind, or dust could send a spacecraft miles off course.
We don't know what the atmosphere is going to be like on the day that we land. That spreads out that uncertainty and means it's really hard to find a safe place that's safe over that huge amount of land.
Curiosity could counter any atmospheric variables during landing using a so-called guided entry technique. 2 weights jettisoned during entry would shift its center of mass. Tilting the capsule would generate lift, a bit like an aircraft wing. Flying instead of falling, thrusters could then be fired to steer the probe towards its pre-programmed target.
And that allowed us to shrink our footprint of where we might end up on the surface from more than 100 kilometers to something down around 20 kilometers or maybe even a little less. And that opens up a ton of places to land.
It gave planners hundreds of sites to choose from. It took them 5 years to pick one.
Of the rim and creation of what is proposed to have been a lake inside Holden.
Dozens of sites were analyzed in detail, and all of them had one thing in common.
Some incised channels.
The starting point was, are there interesting minerals there that we think formed in water? If a site didn't have that, it really wasn't in the running.
Hundreds of experts voted to decide where Curiosity would land.
Boats are in.
Gale Crater is more than 150 kilometers wide. It's also very old and may have once flooded with water. A mountain of layered rock called Mount Sharp rises 5 kilometers above the crater floor. Orbiters detected minerals that form in water in Mount Sharp's lower layers. Its upper layers may also record millions of years of Martian geography.
Geologists, their eyes light up when they see layered rocks because that's the storybook.
Exploring Mount Sharp, we start at the bottom and we go to the top. We drive up through the layers, we turn through the pages and chapters, and we may not finish the book, but I'm sure it's going to be a good read.
They knew exactly where they wanted to go, but to get there, they had to be ready to launch by a deadline that could not be missed. Mars takes almost 2 years to orbit the Sun. Its distance from Earth changes constantly. The ideal alignment for a Mars launch occurs every 26 months, and that moment was fast approaching.
I have had a tradition of pulling out my trumpet as our spacecraft have left JPL. The day that it's put in a box and shipped across the country to Florida is the day it's really leaving to Mars.
The engineers who built Curiosity took it as far as the Kennedy Space Center. A new team took over to reassemble the rover and all her flight components into a spacecraft. 5 months later, it was ready to go, perched on the top of a mighty Atlas V rocket. After a decade of work, all systems were go.
Produce ECS for launch.
Roger. SCS count started.
Status check. Go Atlas. Go Centaur. T-minus 10, 9.
8, 7, 6, 5, 4, 3, 2, 1.
Main engine start. 0. And liftoff of the Atlas V with Curiosity.
Curiosity was on its way to Mars. It was a fine evening at NASA's Jet Propulsion Laboratory. The calm before a meteor storm focusing on a tiny speck in space.
Existed on Mars, and perhaps
The real Curiosity was 250,000 kilometers away, approaching touchdown on Mars. It was crunch time for those who had dedicated much of their working lives to this one mission.
I can't even tell you how excited I am. I just want to remember every single moment.
Mostly confident, but there's still that little nod of fear in there.
Spend 10 years of your life working on one project, and it either works or doesn't. There's really no in between.
In a few hours, hopefully, there's a new rover on the surface of Mars. It's kind of an emotional time, as you can see. We're wishing for the best. We feel that we've done everything to deserve it.
Once the 7-minute pre-programmed landing sequence began, engineers could do nothing. It took 14 minutes for communication signals to travel across space from mission control to the rover itself. By then, it was either safely on the surface or forever lost.
We can't joystick it from Earth. So when we're sitting there, it's kind of a time machine. You're just like looking back at the past, and you're like, okay, 14 minutes ago this worked, and 14 minutes ago that worked.
We've also completed enabling the pyros.
And so it's a very surreal feeling knowing that it's all been finished, but that you still don't know what happened.
These were the final moments before Curiosity was due to slam into the thin Martian atmosphere.
Coming up on entry.
Their so-called 7 minutes of terror had begun.
Start of guided entry. Vehicle's continuing to decelerate. We're down to about Mach 2. Parachute deploy. We are decelerating. Speed shield has separated. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. We are in powered flight. Standing by for sky crane. Sky crane has started. Descending at about 0.75 meters per second as expected.
Tango Delta nominal.
Rib view stable. Rib view stable. UHF is good. Touchdown confirmed. We're safe on Mars. Heads up, folks. Flight EDL images are starting to come down. Stand by for images.
The first crucial images emerged. 250 million kilometers away, Curiosity was sending the pictures that proved it had made it down in one piece, having settled in the freezing sunshine of a Martian afternoon. It beamed back dazzling wide-field vistas of the Gale crater. And it didn't have to travel far before its first compelling find on the crater floor. Intriguing geology exposed by the blast of its landing rockets.
The thrust was so forceful, it blew the soil and the pebbles away, which gave us an opening to the bedrock. We saw that it was composed of fragments of different kinds of material. So the team began to wonder, gosh, maybe it was kind of a cemented material that had to do with water.
It was the first exciting clue about the nature of the ground where Curiosity landed. Pictures taken from orbit suggested water had flowed through a canyon in the crater rim, carrying rocks and sediments across the floor. If so, the alluvial fan may have extended as far as Curiosity's landing site. 5 weeks into the mission, more compelling details emerged.
You're like, my goodness, it looks like somebody got a jackhammer up and lifted up a piece of the sidewalk in New York City. And when you look at the slab end on, you see pebbles in it. They seem to have rounded edges. They've all been smoothed off a little bit. And so what that brings to mind immediately is what you see in a riverbed. As the water pushes the pebbles along, they collide with each other and progressively get rounder.
Previous rovers detected evidence of shallow seas and hot springs. This was new.
The team converged pretty much unanimously on this being an ancient pebble deposit formed in a river that had once been present in this part of Mars billions of years ago.
The size of the pebbles indicated that a vigorous river once flowed there.
This is the first place where we have evidence for water flowing across the surface. That's something we've never been able to discover before on Mars.
Curiosity sampled soils and found minerals similar to those in volcanic soils in Hawaii. Early atmospheric analysis in Gale crater detected carbon dioxide, but no methane. It remains to be seen whether the gas, which can indicate microbial life, is found elsewhere. Curiosity's ultimate destination loomed in the distance. The foothills of Mount Sharp and its layers of ancient rock.
When you see those foothills, it looks like a familiar place. It's like you'd almost come home in a way to a different part of the Earth, except this is Mars.
You may as well be standing out in the Mojave Desert or someplace in Utah. It just begs the question, why shouldn't Mars have life just like Earth? And really, that's why we're here. That's the question we're trying to answer.
It's an answer with a profound implication for humanity. Are we alone in our tiny, insignificant corner of an unimaginably vast universe?
Meet the real-life Donnie Brasco, the FBI agent who risked it all to infiltrate the mafia, when brand new Inside the American Mob continues at 10 p.m. tomorrow.